Let's talk about the dot product. The dot product is one of two ways that we can multiply vectors together, the other being the cross product, which we'll talk about in the next video. We've already tried adding and subtracting vectors together and multiplying vectors by scalar values, and in all those cases, we always get a vector as an answer. But when it comes to the dot product, we don't get a vector as an answer. Instead, what you get as an answer is a single number, what we call a scalar value. So I think the best way to show how we can use the dot product and what we can use it for will be through this example. Consider the vectors vector A equals 1, 2, and vector B equals 4, 1. Now what you notice about these vectors is that they exist in two dimensions, right? They only have an x and y component, not an x, y, and z. And the great thing about the dot product is that you can use it in either 2 dimensions or 3 dimensions. It works the exact same way. Part A. Find the dot product. Okay, so all we're going to do is perform the dot product between these two vectors. Now the way that we do this is really straightforward. All you have to do is multiply the x values, right, the x components of those vectors, and then we add the y values multiplied together, just like that. If there was a third z value in each of these vectors, then you would add those two numbers multiplied together, but we don't have that here, so we can just stop here. Now, if you perform this calculation, 1 times 4 is 4, 2 times 1 is 2, add those together, and you get 6. So, just like I promised, we get a scalar answer when we take the dot product of two vectors. Now, what can we do with this value? Well, that's what we're going to explore in parts B, C, and D. So, that was part A. Part B is asking us to find the angle between the two vectors. In other words, if I have vector A something like this, and vector B is something like this, what is the angle between them? So notice that I've drawn these vectors tail to tail. That's what we're supposed to do here. You connect the vectors tail to tail, and you figure out what that angle theta is in between them. Now, the simple way to do this is by using a formula. There's a great formula that we're given. It is the dot product of two vectors is equal to the magnitude of those two vectors multiplied together, multiplied by the cos of angle theta, where theta is that angle between them. So all you have to do is plug in the dot product you found, right? That would be a value of 6. Figure out what the magnitude of those two vectors are, and then you can isolate for theta. How do we find the magnitude of these two vectors? Well, I think you probably remember, right? The magnitude of vector A is just going to be equal to the square root of 1 squared plus 2 squared. It's kind of like your Pythagorean theorem, right? And if you do that calculation, you should get the square root of 5. You can do the same thing for vector B. You take the magnitude of that, you do the square root of 4 squared plus 1 squared, and if you do that, you should get a value of square root 17. Now you could calculate those and have an approximation rounded off with a decimal, but I prefer using the exact values just to ensure that my final answer is as precise as it can be. Now let me slide part B up a little bit so I have more space. Okay, perfect. Now all we have to do is plug everything in. Remember we said the dot product was 6, so 6 is equal to magnitude of A, which is root 5, times the magnitude of B, which is root 17, multiplied by cos of the angle theta. Once you get this, all we have to do is isolate for theta. So I'm going to remove some of this work I did before. Now let me move this up here. Okay, good. Now how do we isolate theta? Well, you can divide both sides by root 5 and root 17. So 6 divided by root 5 root 17. And you can say this equals cos of theta, or at this step you can take cos inverse of the other side. So the cosine inverse of this, or you could say arc cos of this, will equal the angle theta. Do that calculation, and you should get as an answer approximately 49.4 degrees. And I'm just going to work in degrees here to keep it simple. So this angle, 49.4 degrees, is this angle here. It's the angle in between those two vectors. And again, you could go through this whole process using three-dimensional vectors as well, it would look exactly the same. Now, let's look at part C. Okay, part C says find the projection of vector A on vector B. I'm going to make another sketch here just to help us imagine what's going on. This is your vector A, and this here is your vector B. So what does it mean when it says find the projection of vector A on vector B? Well, remember when we had vectors and you wanted to find the x component and the y component, right? Those were really projections of your vector on the x axis and y axis, or the x direction and y direction. We're going to do the same thing here, right? Instead of finding the x component and y component, what we're asked to find is the component of vector A that is lying on vector B. So not in the horizontal direction, not the x component, but this component here. So if you were to draw a line from the top of vector A downward so that it met vector B at 90 degrees, like this, what would be this vector here? Well, I think we know how to find the magnitude of that vector, right? We have this angle in here, the 49.4 degrees. If I wanted the magnitude, right, the length of this, all I'd have to do is use the magnitude of vector A and multiply it by cos of this angle, right? So we know that the magnitude of vector A multiplied by cos of 49.4 degrees will give you the magnitude of this yellow vector that we're looking for. So the magnitude of vector A multiplied by cos of the angle theta, which in this case is 49.4 degrees, that will be equal to this magnitude. Now this, however, should look familiar, because remember, we have this equation that says the dot product is equal to the magnitude of A times the magnitude of B times cos of theta. Well, you could isolate for this part of it, right, this thing here, and you would see that magnitude A cos theta is actually equal to the dot product divided by the magnitude of B. So yeah, you could use this to figure out the magnitude, or you could use this. And the reason I might use this is because you don't have to worry about taking cos of a particular angle, right? You can just use this thing here, the dot product divided by the magnitude of B. So this will give us the magnitude of the yellow vector. But the question is, how do we find the direction? Because remember, vectors are made of magnitudes and directions. This is only going to give us the magnitude. It's only going to give us that length. So how do we find the direction component of this? Well, remember, it's traveling in the same direction as vector B. So what would I have to multiply this magnitude by so that I get a vector that has that magnitude but is in the direction of vector B? Well, you can multiply it by the unit vector that has the same direction as vector B. Remember, a unit vector is just a vector that has a length of 1. So if we can find the unit vector that goes in the same direction as these vectors here, but has a length of 1, we can multiply it by the magnitude, whatever it is when we find it, and it will give us that yellow vector. Now, how do we find the unit vector that goes in the direction of B? Well, you might remember this from our unit vector video, but all you have to do is take the vector B, right? Take your vector B and divide it by the magnitude of vector B, right? If vector B had a length of 6 and you divided it by a scalar value of 6, you'd be left with a vector that is going in that same direction but is much shorter, right? Only has a length of 1. So this is the unit vector. Okay, so we just have to multiply these two things together. In other words, what we can say is that the projection of vector A onto vector B is equal to these two things multiplied together. And if you'd like, when you multiply these, you can simplify it a little bit. You can say A dotted with B over, well, it's magnitude of B and magnitude of B in the denominator. That'll be the magnitude of B squared. And you multiply that whole thing by vector B. So this is your vector. This is a scalar value. Multiply them together, and you will get your projection of A onto B. So this equation here, this little formula, is very helpful, right? It allows you to project a vector onto another vector, or in other words, find a component of a vector that lies along a second vector. So this is what we want to use going forward. So let me clean some of this up. Okay, perfect. And again, you don't have to go through that whole process of figuring this out. You can just use this formula, okay? I was just giving you the background there. So let's use this formula. The projection of vector A onto vector B is going to be the dot product of those two vectors, which we already determined was 6. We have the magnitude of vector B squared. Well, I believe we said the magnitude of vector B was the square root of 17. If you take the square root of 17 and square it, you get just 17. Okay, so that's our scalar value. And we multiply that by vector B. Vector B is 4, 1. You can expand this, right? You can multiply this coefficient into the brackets, and you would get the vector 24 over 17, 6 over 17. Just like that. So this vector we get here, that is this yellow vector. It is the vector that lies along vector B that is a projection of vector A. So you can kind of think of it like the x component of vector A, except it doesn't lie on the x axis or in the x direction. Instead, it lies along vector B. Now that's for part C. For part D, it's asking us to find the vector component orthogonal to vector B. In other words, it wants us to find this vector here. This is the vector component orthogonal to vector B. That's what they're asking for. So how could I figure this out? Well, let me clean this up a little bit. So I have here my yellow vector, right? We want to find that purple vector next. How can we do this? Well, let's give everything a name, right? Let's call this here maybe vector C. So vector C is that yellow vector. And let's call this purple vector vector D. Well, you can see from this diagram that vector C plus vector D should give you vector A, right? We can say that vector C plus vector D equals vector A. If that's the case, and we want to find vector D, then vector D should be equal to vector A minus vector C, right? You can just solve that algebraically. So vector D is equal to, well, vector A is 1, 2, minus vector C, which is 24 over 17, 6 over 17. Perfect. Now we can figure out what vector D is. Okay, let's do this subtraction. Vector D is equal to 1 minus 24 over 17 and 2 minus 6 over 17. We can make a common denominator for each of these, right? This 1 can turn into 17 over 17. So 17 minus 24, that would be negative 7 over 17. And over here, 2 can be turned into 34 over 17. 34 over 17 minus 6 over 17, that would be equal to 28 over 17. So this is your vector D. It's that purple vector. And if you wanted to check your work, you could check and make sure that vector C plus vector D, those two that you got, do in fact add up to vector A. So hopefully this video has explained what the dot product is, how we can find it, and how we can use it in these different applications to find the angle between two vectors, as well as the projection of one vector onto another. And again, this last part that we did here, this was for part D. I forgot to change that. So hopefully that makes sense.